Hi. Section 3.2, working with derivatives. I know. So how do we work with derivatives? What do they do? Well, we want to consider a graph of the function and graph of the derivative and see the relation between the two. Before I draw anything, I'm going to write in blood over here that derivative measures the change. This might be the single most important sentence in understanding derivatives. If the system is changing, doesn't matter the amount. If you have sufficiently precise equipment to measure, you can detect those changes, and those changes can be modeled by calculus. What types of changing things you have in the environment? Is there anything changing with this bottle? Apparently not. Of this bottle? No. Right now? Oh yeah, it's speed. Okay. Sure. We can change the speed using acceleration. But then you can change population, right? You can change the amount of fuel as you drive, because the amount of fuel is being changed, right, burnt and changed into energy, which propels the car at 27 of the whooping 27% efficiency, right? I know. We advanced as a species.
Our enthusiasm is 5 hours drags on.
There you go. The change in enthusiasm. I show up in the morning at 8:30 and I say, "Hello, everyone." And it's the same when I leave. It's constant. It's constant, no enthusiasm.
Oh no, it's a microscopic change in the negative.
Oh, there's a oh yes, because 5 hours elapsed. Yeah. And then your height throughout the course of the day. You're tallest when you wake up. And then your weight will be compressing your joints slightly. So fraction of an inch throughout the day. And then when you become horizontal, right, and you sleep, everything relaxes and you grow. You wake up in the morning, you're tallest. The weight, same deal but the opposite way. You're lightest when you wake up in the morning, and then you eat throughout the day, and then you burn that stuff for, let's say you sleep 6 to 8 hours. And then you wake up, you're lightest. So these changes that you can't see, but they're there. As you drive, as I said, you use up the fuel. If you are to lift the chain from the floor, the piece that you are lifting is progressively heavier because more and more links are lifted off of the floor. Right? You're lifting one end of the chain, the other end of the chain with a lot of other chain is on the floor. So as you're lifting one end, the higher you go, the heavier it is because more links are introduced and each one of those contributes to the weight. So derivative measures this kind of change. And we have change in all kinds of sciences, obviously. Engineering and economics, everything. So these derivatives will measure, naturally, would measure a lot of stuff. Sometimes it is much faster for us to look at the graph of the derivative rather than graph of the function itself. Because graph of the derivative can reveal certain aspects faster. But in order for us to see that, we have to take a look at few graphs of functions and derivatives and see how they're related and what this derivative actually tells us. So say we have a function like this. What I'm going to see here is that the change, what is the slope of this line? Is positive 1. Because you go 1 square over, 1 square up, 1 square over, 1 square up. So the slope of this line is 1, which means that the derivative is 1 on the same interval, negative infinity to 0 on x-axis. The function has the slope of 1, which means the derivative, we said the slope is there. Now how about the constant piece? 0. The derivative is going to be 0 here because common sense. How much change do you have within a constant? No change, right? So derivative is 0 because there is no change. And then we have the negative 1 slope, which will give us negative derivative going to infinity. So now you consider the function f of x in black and f prime of x, the derivative. Oh, you can see so many cool things here. Observe that while function is increasing, meaning going up, the derivative is above x-axis. Derivative is positive. Where function is constant, derivative is 0 because there is no change. And when the function is decreasing, the derivative is below x-axis. So if I am to look just at the derivative, let's say there is no function, there's no black line at all, I would know that up to 0 function is increasing. I would know that function is constant between 0 and 4, and I would know that function is decreasing afterwards. I wouldn't know the values of the function, but I would know the general shape, and then I get to, move that one up and down with the plus minus c. So you have to start learning here because the next graph is going to be curved. This one was very easy because the slope of this line, this is a linear line, and the slope is constant, it's positive 1. So the derivative was not an issue to draw. But then we move to an arbitrary function. Let's talk about, say, x squared. You can always consider the slopes of the tangent lines. You can draw little tangent lines. Hopefully you guys can see 3 parts of this graph. I'm going to isolate the peak, right, the minimum value, and then I have the 2 branches on sides. So if I draw little tangent lines here, just to see what's happening, I would see that I have that slope is negative for x is less than 0, slope is 0 when x is 0, and the slope is larger than 0 for x larger than 0. Well, there's one-to-one correspondence for these. So I'm going to say this slope will be below x-axis on derivative graph. We all understand that x equals 0 is on the x-axis, right? And this is above x-axis on the derivative graph. What you have here in the minimum is horizontal tangency. What is the horizontal tangency? Horizontal tangency is this horizontal line where slope is 0. You will always have that when you have min and a max. See? The max has the horizontal tangent line there. Min has horizontal tangent line there. Horizontal tangencies occur at every min and a max. So how do I draw the derivative now? Well, I have my x squared. The derivative of this is this guy. Let's think about it. The function on this part is decreasing. Decreasing means derivative is below x-axis. We have 0, 0. It coincides with the derivative there. And then you have a positive branch here, which is increasing, which is the increasing part, which is above x-axis. So when you're looking at x squared graph, you have this particular derivative. Now, I did tell you earlier that derivative of x squared is 2x. So this is your 2x. It's a graph, 2x. It goes 1, 2, and over 1, and so on. What happens if we have more complicated graphs and more complicated derivatives to draw? Tip. Vertical asymptotes vertical asymptote locations are preserved in a derivative, in the derivative. There's only one derivative for function. What this means is that if you have a vertical asymptote at x equals 0 for a function f of x, your derivative must have vertical asymptote at the same x equals 0. If function had the vertical asymptote at x equals 5, the derivative will have vertical asymptote at x equals 5. That's the meaning of this tip, that vertical asymptote locations are preserved as you go from function to the derivative. It will come in handy. Let's first consider a graph. Whee! There we go. I hope that you are immediately observing 2 max value and 1 min value, and then these guys go to infinities, right? Do we all observe that? I'll put a dot right there, a dot right there, and a dot right here. This is where we have horizontal tangency, whose slope is what? 0. M equals 0, all of this. So all of these have m equal to 0. That means that if you're drawing the derivative, these points here are the points where the derivative will cut through x-axis. It has to, because the slope. Now, these points also, I will erase this. These points also partition the world for me right now. When I partition the world this way, I'm going to move y-axis to make it nice. If you look at these purple lines, they partition the world into 4 regions. There is a region negative infinity to whatever the hell this point is, and then from this point to the next, from this point to the next, and then from that point to infinity. So it's like cuts. The derivative in each one of these is going to be considered separately. We don't have to consider the entire function at once. Because we know if the function is increasing, we draw a derivative above x-axis. If the function is decreasing, we draw a derivative below x-axis. And if we have min and max, that's what it cuts through. So look what I have to the left of the first purple line. Do I have increasing or decreasing function? Increasing. Which means the derivative has to be positive. So I'm just going to put f prime bigger than 0 for this region. How about the next set of purple lines? Decreasing, therefore derivative is negative. Good. Which means below x-axis. How about the next part? Very good. And how about the last part? Excellent. Oh, look at that. That's cool. Increase, decrease, increase, decrease. Nice. I can draw this as a nice squiggle, right? So I know that the first part of the derivative to the left of the first purple line has to be, derivative has to be drawn above x-axis. So derivative is above, derivative is below, derivative is above, derivative is below. Now you might ask, how do you know how tall do you get to draw a derivative? And the answer to that question is, I don't know. It's a sketch. It doesn't matter in this case. And if you push me, I'm just going to teach 4.3 then. All right? Because that's what you want to know. So how tall or how shallow I'm going to go with this peak is irrelevant for the section we're in right now. You are learning that graphs and derivative, right, so the function and its derivative, are joined together in a bond that cannot be broken. What derivative is going to do is governed by the shape of the function. When function has min and a max, the derivative must go through 0, because the slope of the tangent line at those points, which is what derivative portrays, is 0. There's no debate there, or opinions, or feelings. It is you sitting down and actually figuring it out. The black line is the function, the red line is the derivative, the black line has the horizontal tangency at these 3 points. Those are the zeros for the line. And you keep going.
I'm kind of confused about why the derivative starts from the positive even though the function comes from the negative.
It's a very interesting question. Why the derivative starts from positive where the function starts from negative? What we have to consider here is the change. If you are looking at the the black line, which is the function, you see that the black line came from negative infinity. Now, imagine yourself with negative infinity of money. You know what that means? That means that it's so terrible that you can't even sign up for a cell phone, all right? So you never made any money, no one ever gave you any money, and anything that you are buying or having is piled up onto a debt, and that debt is infinite. I'm talking about everyday food, clothes, gas, education, anything that you can possibly imagine. You don't have a penny, not even a penny. So it's infinite debt, infinite debt. So now, consider the change from having the infinite debt to having $1,000 in a bank. Do you see how that change was infinitely positive? From not having anything to having $1,000. Yeah, $1,000 is still worse than having 100,000 or a million, all right? But it's still infinitely better than being infinitely in debt. So you are not going to consider point by point. You have to consider, you have to look at the red function as a measurement of the black function's change. So it's, should I say philosophical answer? I don't know. But if I'm infinitely in debt over here, and then I go and I have $1,000, this over here shows that the change, right, is positive. Because it's changed to a positive situation in my life. And then following is me spending the money and not having as much, which reflects as a negative change in my life. It's a measurement.
But wouldn't like it coming from the positive look like a negative change? That's what I'm confused about.
What do you mean negative change?
From like right where you wrote the derivative prime, how it comes like swoops down. Wouldn't that be negative since you're reading it left to right?
Well, for the red line, the only thing that is important here is whether it's above or below x-axis. Because if it's above x-axis, positive change. If it's below x-axis, negative change. So again, I have no money, and then I have 1,000 in the bank. It's above x-axis, a positive change.
So right now, we're just concerned with the fact that it's above the x-axis.
Yes.
Okay.
Yes. Again, you might want to push further, and I'm going to say now 4.2. We learned about concavity, we learned about increase, decrease, and all that good stuff, and that tells you how fast you write and all of these other things. Now, we are going to consider a graph with the asymptote. Say you have good old 1 over x, whose shape you must know, memorize, right? Here it is. So the black one again is this. So now you're looking at this graph and you say, all right, for the derivative, I have to preserve vertical asymptotes. Vertical asymptotes, we know from previous chapter, right? They're defined through that limit. You asked it. The vertical asymptote is defined through the limit, and we say it cannot be crossed ever. Great. The thing that I wrote earlier in purple said that the vertical asymptotes are preserved. So both derivative and the function will have a vertical asymptote at 0. Let's draw the derivative. What do do I know about this piece of the graph, the one on the left? What do I know?
Negative change.
It's negative change. Very good. All slopes of the tangent line that you draw will be negative. Negative, 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 negative. All of them have negative values. You can see that the entire part is negative, therefore it goes below x-axis. So I draw a piece that looks like this. It looks pretty much the same as the original function. How about the second part?
Also, negative change.
Aha, negative change as well. So, also underneath. So now looking at the black and red and trying to make sense of this, right? Well, first off, if you're just learning the mechanics of how to do the problem, vertical asymptote is preserved, and just make sure you follow it, right? You see that this is decreasing. Decreasing means negative change. You had this much money, then you had this much money, then you had this much, right? As the time goes on, for this graph, you have, as time goes on this way, you see that you're constantly having less and less and less and less and less. That's all a negative change. Put the money on this side. You have $1,000, right? Here you have $1,000, and then you have $500, and then you have $100, and you have $50, and you have $25, right? See that? It's again negative change. So negative change again has to have the derivative below. Now, if I am to ask you to compute the derivative of 1 over x, you would crank that terrible, terrible limit thing, and you are going to arrive to the function f prime of x, which is negative 1 over x squared. Hey, that's the red graph, right? Because it is negative. So the derivative here is going to be negative over 1x squared. So this guy is this. If you remember my lectures earlier on derivatives, on asymptotes and stuff, I did have 1 over x squared somewhere, and it looked like this. So this is a negative 1, it's just below. So it's, again, all of the aspects of math, right, together, they are everything you learned before is there. And then we run into this issue where you have no derivative. Derivative does not exist. At which point you will say that the function is not differentiable. Something that you have to pay attention to. Let's talk about the simplest example in a galaxy, which is the function absolute value of x. So generally, these absolute values are going to make stuff not differentiable. Let's see why and how. So f of x is equal to absolute x. And you draw the V shape, right? You draw the V shape. So now, you know that you have a minimum, slope is 0 there, right? Well, let's think about it. And then what else you have here? Slope is 1 and slope is negative 1. So look what happens when you try to draw this. Slope is 1, that's this thing. Slope is 0, that's the dot. And then this one. Do you see how the derivative wants to be both 1 and -1 at the point? The derivative doesn't exist. It's not 0. The derivative does not exist. Remember what the slope of the tangent line requires. It requires the limit as h goes to 0 from both sides to give you a value. Well, wouldn't you agree that as x goes to 0 from the left you get +1 and from the right you get -1? And by the theorem in chapter 2 we know that that does not exist. So in this case here, derivative does not exist at x equals 0. Because the derivative at x equals to 0 just tiny bit to the left is 1, and a tiny bit to the right is -1. And those are not the same values. Right? We talked about the limits. We talked about the left approach, right approach. They all have to converge at the same point for us to claim the limit. Now, the derivative is defined through the limit. If the limit does not exist, common sense, the derivative is not going to exist. So, we can claim the same thing that we claimed for continuity. This graph is not differentiable, but it is piecewise differentiable, right? The same thing you have for continuity, that global continuity, right? So the function is not continuous, but it is piecewise continuous, right? You take a little piece and a little piece, right, and so on. So this particular function not differentiable because there is no derivative at the peak, at the 0. Now, I talked about minimum, maximum, and this one looks like, well, you should have the 0 there. I don't, because it's a spike. When it's rounded, I have it. Because when you are going up the hill, right, you're going up the hill, it's not a spike, it's a hill. So you cover every single slope, you get to that 0, and then every single slope. What is happening as you are going to the peak? You are going at -1, and then all of a sudden 1, right? That makes no sense. You can't be -1 and 1 at the same point. Not differentiable. Anytime when you have these spikes and cusps, right, you are going to have this situation. Another famous example would be sine and cosine graphs in absolute value again. So this time we have absolute sine x. We know from our review that the first two would look like this. See this part over here? No derivative there. At that point. No derivative. Because these guys, right, are having, now this is going to be a vertical tangent there. So when you're looking from the left, you are going into the negative infinity slope. And you're looking from the right, you're going to the positive infinity slope. Negative infinity and positive infinity are not the same on the 1D line. Bend it. So there is another part where, again, absolute value most of the time does this as long as it reflects something, you know, abruptly up. It's bound to make these sharp corners and cusps and things. So generally, these guys are going to be piecewise differentiable, but you say for the entire function not differentiable because it's not differentiable at, in this case, pi, previous case 0, and so on. So you have the notion of not differentiable at the point. And that happens when you have a spike or you have a cusp, which is kind of trying to go into infinite slope, which is the verticals. Yes?
Does that mean like we cannot find the overall formula that we did before with the problem?
You can find the overall formula. The overall formula for the derivative exists.
Okay.
If I go to the previous example where it's easy, right, for you to understand, because we haven't covered yet derivatives of sines and cosines, but over here, the derivative, I can write it, but it's a piecewise function.
But not at
You see, it's 1 for all x is less than 0, and it's -1 for all x is bigger than 0. This is actually your derivative. It's not going to be the nice 2x plus 1 that you're used to from previous section. It's going to be piecewise function. Same thing goes here. Right? It's going to be a piece and another piece. Cool? Of course, math. One more concept and we're done. No more lectures. 3.3, 3.4, 3.5 for next time. Right? I believe we are left with 10 classes, guys. And then the final. You are going to see me 10 times. Me. 10. That's it. And then final. So 3.3, 3.4, 3.5, and do whatever you can from the lab. 3.1 and 3.2, so you can have some lab time and hopefully start talking to someone. Yeah. The last thing that I want to mention is the connection to continuity. And this is a useful theorem for some proofs, and again, mainly used in honors, but it's one of the really, really large theorems, so you need to know it. And it says if f is differentiable, then f is continuous. So if f of x is differentiable, at x equals a, then f of x is continuous. At x equals a. It is a major theorem. You can do a lot of this. Obviously, you want to see if the function is continuous. This is how we get. You remember how you had to memorize if all polynomials are continuous? Well, think about it. Do polynomials have vertical asymptotes? No. X squared plus 3, x cubed minus 1. These are all polynomials. They don't have vertical asymptotes. They don't have jumps. They don't have spikes and cusps, nothing. They're smooth and they just do this all the time, right? So, they're differentiable everywhere because they don't have vertical asymptotes and they don't have spikes and cusps. Therefore, by this theorem, they're continuous. You see? So, you memorized earlier that e to the x, ln x, and then polynomials, sine and cosine, you memorized that those guys are continuous, and that was a theorem. How do you prove each one of those? You use this theorem, right? And how do you prove this theorem? You look at the book, it's done. You define special function, you multiply it into, and cancel some terms, and voila, there you go, works. So it's about 5-6 steps. It's all outlined if you're interested in a proof. Again, not honors section, so we're not going over the proof. But you see how stuff builds up, and you're not allowed to skip a step because you can't connect all of the things. So you would take a look at the polynomial. You would see that polynomial, no matter what order polynomial you have and how many terms it has, you see that it does not have vertical asymptotes. You see that it doesn't have spikes and cusps and stuff like that. And you claim immediately it's differentiable. You use this theorem, and because it was differentiable, it's continuous. Sines and cosine work the same way. Tangent, not so much, right? Now, is tangent going to have a derivative? Well, yes, it's going to be secant squared of x. But again, you have to consider the domain. The derivative preserves the vertical asymptote. Where is the vertical asymptote for tangent? Vertical asymptote for tangent is at pi over 2. Where is the vertical asymptote for secant? 1 over cosine. Also at pi over 2, because cosine goes to 0 at pi over 2. Everything always fits in perfectly, like Legos. You will not find branch in mathematics where you figure something out in math and it contradicted something that happened before. That cannot happen. We have other areas of human endeavor, like politics, so you can have those kind of exercises, right? Where you say one thing and it contradicts the other, and then nothing makes sense, right? Perfect, right? But in math, never gonna happen, all right? Figure out one thing, everything that was figured out for centuries before, you figured out that one thing, everything else fits in perfectly. If you take linear algebra, you know what I'm going to do in linear algebra? You're going to take the entire Calculus 1 class and write it in a single line. Yeah, that's your linear algebra class. It's awesome. If you can imagine that you can put Calc 1, Calc 2, and Calc 3 in a single equation. And differential equations, well, linear ones. One equation for all of it, all of it. It has this property and the previous property, all of limits and all of derivatives and all of integrals, everything in one equation. And then you generalize that later on. That's what math is, right? So cool. This is all we have for working with derivatives. We see that we can work with derivatives to give us continuity. We definitely see that we work with derivatives to discover the minimum, the maximum, right, which will be applied later on. We're going to come back to this lecture and the first 3 sections of chapter 4, and we are going to feed off of this a lot, where we are going to use it to find exact location of min and max, and increase, decrease intervals and concavity and stuff like that. So this lecture is not just, okay, 3-2, and I draw some pictures and it's cool. We are going to use every concept from this lecture, particular 3-2, to build up 3 sections, 4-1, 4-2, and 4-3. The homework, if it's not open, will open. The exams will be returned next class. We do not email grades. So do not send me an email about, if you stop by my office hours, let's say Tuesday, Wednesday, Thursday, I have office hours every day, and you ask, did you grade the test? I can tell you. If I graded the test, I can tell you the grade, right? Because that grade would be already in the system, and I can tell you. Now, you will get the exam on when, because I'm not going to have the exam. Let's say I grade everything tomorrow. I am not going to have those exams sitting in my office, because tomorrow I'm not in my office, right? They're going to stay probably in my house, and I'm going to forget them on Saturday morning, drive back to pick them up, and then be late for class, because it's usually what happens when I have to return exams in this class. So if you guys stop by and I'm done grading, I will tell you the grade. If you send me an email, I will erase it, because I don't know who's reading the email on the other end, right? Maybe someone figured out your account and is going to blackmail you or something. If you stop by, I'll tell you your grade if I'm done grading. Questions, concerns? Let me just shut this off. Bye, stream.